YOLO composing gloves here, and today we're going to be talking about frequency. Frequency is the number of times some event occurs. So for example, if I go out today and kiss 5 amazing people, then I will have a frequency of 5 for kissing amazing people. And notice that I'm counting this in a per day. I could do per hour, like kiss 5 amazing people per hour. Now, if I go out the next day and I kiss 20 amazing people, then I'll have a frequency of kissing 20 per hour. So my frequency the next day would be 20, not per hour, per day. I'd have a frequency of 20 for the second day and only a frequency of 5 for today. So that's frequency. It's the number of times something happens. And in this case, we are using the version that includes a period of time. There's another kind of frequency you can actually use, like per length, like how many times does something happen per meter. And there's just other ways. Now, music, we want to use a per time kind of way, because we are interested in how many times a specific waveform happens per second. Now, specifically when we use per second, we use the unit called hertz. So hertz is how many times something happens per second. So for example, here I have a waveform. This is a sine wave. It is what's called a pure frequency. And all that means is when I play it, there's only one frequency. This will make a little bit more sense later in this video. So here I have a sine wave. It starts at 0, it goes up to a max, back down to 0, goes down to a minimum, and then comes back up to 0, and it repeats this. And however many times it does this per second will be its frequency. So if I do this, for example, humans can hear this, if you've got like really great hearing, 20 times per second or 20 hertz, that's a frequency. If I play it, you can see it down there. You might be able to hear it, you might not. I have a hard time hearing 20 hertz. If I go up to like 100 hertz, if you have good speakers, you should be able to hear this. So here's 100 hertz, and all that's happening is this is playing 100 times per second. If I go up to say, let's go up to 9,999.99. So you can actually hear up to 20,000 hertz, and you'll hear it said as 20K, and the K stands for kilo, and kilo stands for 1,000. So when you hear 20K, that's 20,000. And so you'll hear 20 kilohertz or just 20K for short. It's sort of the lingo. So like 6K is 6,000. And this is not unique to hertz. Kilo is just a general thing that works with units. So you could say like 20 kilometers and everyone know, oh, that's 1,000 meters. That's what it means. So here I've got a really high frequency. It's quite ear splitting. Most people can actually hear up to around 18K. You'll hear the standard 20 hertz to 20,000 hertz. Hearing 20,000 hertz is just kind of like you've got dog ears if you hear up that high. Typically, it's really only up to about 18K for me currently. As you get older, this tends to go down. So maybe if I was younger, I'd be able to hear even higher. That's why those teenagers have those mosquito ringtones that supposedly you can't hear if you're over 25, because by then your hearing loss has gone down, so you can't hear this really high tone. Doesn't necessarily hold. I can still hear that tone, so be careful where you use that. But that's the notion of it. So when we have something that repeats like this, we call it periodic. And periodic's important because when we talk about frequency, it's the number of times this period happens per second. So if I come in, I have a graphing calculator here. I'm going to open up another one. We're going to go to Desmos. So this is desmos.com. It's a graphing calculator website you can use. And I'm going to type in just a simple sine wave, which is the same wave. Don't worry about the math. And I'm going to make an adjustment here and give it a step of pi. So we're counting in units of pi. Also, don't worry about that step. It's just something that's going to make this a bit easier. So here I have a frequency, and this frequency is in units of length. So for example, from 0 to the length 2 pi, which is just a number, just remember that this happens one time. And our frequency is right here. If I type in 2, we see that 2. So here's 0 to pi, there's 1. And then if we go one more time, we get to 2 pi. So now we would say over this length, we've increased our frequency from 1 to 2. And of course, I could go more, 4. And we could take a shortcut and just count the peaks. So we have 1, 2, 3, 4. And then we're at 2 pi here. So we have a frequency of 4. This works out for anything that is periodic in nature, meaning it repeats. So for example, this repeats, so that will be a period. And so we can talk about frequency in this way, in a meaningful way, by just saying, oh, how many times does this happen? This repeats. This is a triangle wave. It's repeating though, so we can say, oh, what's the frequency? How many times does this happen per second? This, pretty much anything we do in here, since it's just gonna repeat as I play it, you know, that repeats. Let's bring it up to 2. So that repeats, that repeats, that repeats. So these are all gonna have a frequency where this is just the number of times per second. Now you might be wondering, what about something like this, where it's crazy? It does not repeat. Look at that, it's just nuts. Does this have a frequency? Well, yes and no. Here I'm going to refer you to the Appendix A, where I dive into the calculus of the subject, because we actually have to talk about instantaneous frequency and instantaneous phase, both of which are topics I don't want to dive into here, and we're probably not going to talk about them in the series, but I've included them in the appendix for those that are interested. So this thing, though, we can sort of talk about it as if it had a frequency. To demonstrate this, we're going to go back to the graphing calculator, and I'm going to look and show you this. So we see here that it's drawing a sine wave, and we see that it correlates to this circle. And so as this triangle, you see it's making this triangle right here, and it's moving around. As this triangle moves around, it draws this. And if this triangle were to move faster, we'd have a higher frequency. If the triangle were to move slower around the circle, we'd have a lower frequency. So it turns out that, hey, look at this, sine waves are actually these triangles moving around. And we see that as it moves around, there's an angle. And this angle is what is making every single specific point on this green wave has a specific phase angle. So this angle right here that it's making, and it's defined by this line right here, this blue circle, the little one. This is called the phase angle, and each little phase angle here correlates to a spot on this wave. So when you look at sine waves, you can see them as these phase angles, which is a triangle spinning around a circle. Now, if this is a little overwhelming, don't worry too much about it, but I want you to have a broad scope of where this works, because when we look at something like this, well, it turns out that there's a fancy math technique that you don't need to know how to do, but it's useful to know that it exists. And that is, it's called a Fourier transform. And what it says is, hey, you know, this crazy thing that doesn't repeat doesn't look like it has a frequency of any kind, because it doesn't repeat per second. But it turns out you can write it as an infinite sum of sine and cosine waves. So this sine wave, maybe there's a sine wave in this one here, and we could say, oh, okay, well, maybe this is some sine wave, and then we could add another sine wave to it and another sine wave to it. And eventually we'll actually, when you add them all together, and some would be louder than others. So maybe a sine wave of 20 hertz, one of 1,000 hertz, some 500 hertz, you put them all together and you'll get back your original signal. And in reality, what it corresponds to is basically a bunch of these circles spinning around with their triangles moving at different speeds. And when you put them all together, you get back this. And we can map that. We can map each one of those individual frequencies and how loud each one is. And when we do that, that's called a spectrogram. So let's look at a spectrogram, because this brings a couple important concepts up that you will use and you will see all the time. So I'm going to bring up one of the most common things you see this in. That's an equalizer. So here's an equalizer. And if I play this, we're going to see all the individual frequencies, every single one of those little sine waves. And then if it's a brighter red in the spectrogram, then that means that one is louder or it has a higher amplitude. And then if it's a little faded, that means it's got a lower amplitude. In this particular spectrogram, if I play it, so you can see, we see our spectrum. I wish I could freeze this. There might be a way to freeze it that I don't know about. And we could see that our spectrum is right there. It's right in front of us, and it's using this technique called a Fourier transform. But again, you don't need to know how to do it. You just need to know that's what's going on. And so when we say, does this thing have a frequency? Does it have a frequency? We can answer that question now. So I'm going to open up a different spectrogram. So this is a different kind of spectrogram, but again, it will just display for us. Here we have the frequencies on one axis, and you see they are in hertz, and we have how loud it is on this. Now, this is called the magnitude, and the magnitude is just the length of some quantity. So in this case, it's in decibels. We'll talk about decibels in a future lesson, but basically how loud. So we have frequency and how loud. And if I play our wave here, we see that we have it pop up, and this is a 3-dimensional view. And see, we have our time right here, so this is a bit different. And our frequency, we have 3 axes on this one. So like how high it is how loud. This is over time, and this is the frequency. So it's a little bit crazier. You're usually going to see spectrum analyzers. There are free versions of this out there as well. And so we can see that we have a very high low frequency and some of these other ones. And if we were to add them all up, we get back our original sound. And what this means is we can affect different areas of the spectrum while they are sine waves and then put it back together. And we will get an affected version that will ideally suit our needs better. So we're able to mix the signal. We can come in, make adjustments, and then put it back. Now, does this thing have a frequency? Well, let me pull open another one this one's actually free. It's called Signal Analyzer. And we can use this to determine if it has a frequency. And I'm picking this one because I can freeze this one. So here we go. So we say, okay, here's our sound. And there's a bunch of frequencies up here doing stuff. And this is characteristics of noise, which is typical in snares. But we see here there's a lowest frequency that is pretty loud. And our ear picks up on this. And this is the pitch, in this case, of the snare drum. Or we would call this the frequency of the snare drum. And the reason is because you can actually do this with a bunch of other stuff. So here's a complex wave, but it's periodic. So it's not really complex because it's a periodic wave, but it's going to have a whole bunch of extra harmonics in it because this isn't a sine wave. And so how would I get this waveform? Well, I can actually come in here and say, hey, convert to sine harmonics. So it'll actually tell me. And here's what it would look like. We're not going to talk about these, but these are basically phase shifts. We'll save that for the phase video. These are how loud the harmonics are as we go up. We see they get soft very quickly and that there's one that's really loud. This is really typical of frequency. So this note here, that is the loudest and the lowest, this is what we call the fundamental frequency. Now in some sounds, such as the snare drum, this gets a little political on, is it a fundamental or not? But here, since it's periodic in nature, this is going to correlate directly to the frequency. And we see here on this spectrogram that this right here is our frequency, which in this case, let's play a different note. Let's play like, I don't know, 183 hertz. Let's go a bit higher, 261 hertz. So here it is, 261 hertz. That would be our frequency in hertz because that's how many times this is happening per second. It also correlates to the lowest frequency. So the fundamental is really important for the tone of a sound. The first couple of harmonics are really important for how a sound sounds. Our ear picks up on this and uses it to identify the sound. So for example, if I were to play this and remove the fundamental, it changes the sound quite dramatically. Because this frequency as being the fundamental and defining really the pitch of this particular sound, that's going to be a big deal when we move that or change that or move that around. So that's the name of the game, getting those things in the right spots and making those things fit together nicely. If two things are covering each other up in a sound, if it's their fundamentals that are fighting, we're going to notice that a lot more than if just in general the higher frequencies are fighting. Now there are other things that come into play, which are series of harmonics. We're going to talk about this in another video, but like saw wave and square wave, like we have here, if we go to a square, if I play this, you'll notice a very specific pattern. So there's this really specific pattern, and if I convert it to sine harmonics, we say, oh, look at this. This is an interesting deal here. And there's another one, if I go to like saw, this pattern is another really specific pattern. So we're going to talk about these patterns, but they're collections of frequencies that when you put them together, they result in pretty specific things. One other property of frequency we need to bring up here is size. So frequencies have size because they're really wavefronts of pressure, because we talked about this in our sound video. So let's really quick do a couple examples. I want to show you something. So if I had a really low frequency, how big would it be? And it turns out there's an equation that relates them, and it's really easy. And here I have it in plain English. The size of a wave is equal to the speed of sound, so how fast the sound moves, divided by the frequency. So let's do an example. I'm gonna call the size of a wave S, just for simplicity. So S is equal to the speed of sound, if you remember from our sound video, is 1130 feet per second. I'm not gonna write the units, but remember there's feet per second. And we're gonna put a frequency in of 20 hertz. Now remember that feet per second, and then on the bottom is hertz, and that's a unit in per second. So how many times per second? And it ends up canceling out with the seconds up top, and we are left with just a unit in feet. Now, I'm sorry I'm not using the metric system here, but that's because my unit of speed of sound is in feet already, and I'm used to using this unit, so I'm going to stick with it for now. Let the plague of the imperial system continue forward. So 1130 feet divided by 20 ends up being 56.5 feet. And so we see here that 20 hertz is a pretty big wavefront. And this means that, for example, if I want to stop a low frequency, I'm going to need a big thing because it's a big thing. If I put like 20 hertz and put my glasses in front of it, I don't know if this is on the screen or not, but if I put my glasses in front of it to stop it, it's going to have no problems getting through this because this is really tiny compared to the size of the wave. In fact, for example, here I have my iPad, and if I put it in front, let's do one more before I do this. So let's move this over here. So let's do another one. This time, let's do one with a higher frequency. So let's say that we want to know the size of the waveform of, let's just do 6,000. So we're going to do 6K for short, which is 6,000 kilohertz. And if we do this one, we get S. We need a calculator for this one. This is 1130 divided by 6,000. And we get 0.189. It's rounded. And so here we have like a really small number. Like, look at this. This is 56 feet. And this one's like not even close to a whole foot. And so we say, okay, this is pretty interesting. So this means that things like glasses that have a thickness that is rather large compared to this. Well, not this. I need an even higher frequency for my glasses to really affect it. So this wouldn't be a very good absorber or reflector or whatever we're putting it up for. But for example, my voice is composed of a whole bunch of frequencies right now, right? I've got low ones and I've got really high ones, and that forms my voice. And we now understand that it's a bunch of sine waves. We could talk about it as a sum of sine waves instead of this crazy fluctuating thing. And if I put my iPad in front of it while I'm talking, we're going to hear some of those waves get through because they're big compared to this, while other ones will not get through. So here I am talking, and there should be a pretty significant difference because, you know, this thing is rather absorptive. So there's just an example of how frequency plays into the role of acoustics. And we're going to talk about this more as these lessons continue. So now we know how to talk about frequency with really crazy things. I pointed you to the Appendix A. I've told you what hertz are. We've explained the spectrum and what a fundamental is and how we sort of look at sound from that perspective. We've talked about the size of things. There's one more thing we want to talk about, and that is noise. There are two types of noise you're really going to need to know about, and you may have heard of these noises. We talk about them typically in colors. So there's white, brown, red. There's all these different colors of noise. The two we care about are white noise and pink noise. The others are important, but I'm just not going to talk about every kind of noise in this video. So here I have an example of white noise. If I bring the noise feature up here and play it, we get white noise. And there's a special property of white noise. White noise has equal energy per frequency. So you might be going, does it have a frequency? Well, we'd say, well, it does, sort of. It has equal energy per frequency. What does that mean? It means no frequency has any more energy than any other frequency. And it ends up sounding like that. That's what it sounds like. Now there's also pink noise. Let me give you an example of pink noise. Now this is equal energy per octave. So remember, white noise was per frequency. This is per octave. Now let me contrast that with white noise, which is equal energy per frequency. Sounds a little bit more like the ocean. Now, pink noise and white noise are useful for a whole bunch of sound design things and also measurement purposes. Very important in calibrating equipment. Now I use the term octave there versus equal per frequency. So you might be going, what the heck is an octave? So we actually hear frequencies in a log base 2 kind of way, which means we hear it in a times 2 kind of way. For example, if I play for you 200 hertz, now let's say I want to play for you the next octave above that, which is to say it's the same note, only higher. So I say, oh, what note would that be? Well, that would be times 2. That would be 400 hertz. And if I wanted to play for you the octave above that, I would play for you 800 hertz. This is really important when it comes to tuning systems. I'm not going to dive into it all here, but basically tuning becomes a bit tricky because we hear in this sort of ratio kind of sense. And so a bunch of tuning systems developed, and the piano's actually got a whole bunch of different options. Typically we use what's called equal temperament, which means things are slightly out of tune, but it's in tune enough to be nice. It gets a little confusing there. We'll worry about tuning systems and how we perceive things later. But when we say an octave, we're talking specifically about a times 2 kind of thing. And this can be important for us as humans because since we hear that way, it makes sense for us to take measurements that takes this into account. And that is what frequency is in many of its fundamental properties. If you have any questions, go ahead, drop them in the comments. There's also the Sound and Synth Basics book, which is in the description. You can check it out and read this section on frequency. It's very thorough, thought out. I have lots of links to additional sources, as well as some exercises you can try out to make sure that you really understand the material. And have a blessed day.